And we start with our 2 pieces of advice because they're still the same. You should do problems. The more problems that you do, the better that you'll get. And you really, now that you go back, you're going to go back and say, you know, this stuff at the beginning of the semester, it wasn't so bad. And it's not because it was so bad in comparison, but it's because you've had time and you've actually, unbeknownst to yourself, you've had time to think about things, and you'll discover that you're better at that than you thought you were. Of course, you should still review. You should still do some problems. You have old exams. You have this review. There's also some reviews from recent semesters. You know, these are almost always different problems that we throw in. Now, every semester is slightly different for what's on the final, so not every review problem from previous semesters are ones that you have to do, but you should do as many as you can. The more that you do, the better that you'll get. And of course, take care of your health. You know, that includes mental health as well as physical health. I know that the final exam season can be very stressful, and a lot has to happen in the next 2 weeks. I appreciate you taking the time today so that you can sort of like spread the stress out and hopefully be all right. If you need to take a break and go outside and yell for a few minutes, that's all right. There's a really big open space in the middle of campus. Nobody will hear you. So, all right. With that, let us jump in. Now, number 1, you can probably guess why we want to do something like this. So, you might see a similar question in the most definite sense of the word might. Determine if the following statements are true or false. And no justification is required. Now, on an exam, we would actually have you circle something, true, false. And so here we'll actually write down words true and false. So part A, so let's start with that, says, suppose you have a sum from 0 to infinity of a sub n, and it equals L. That's the value of the sum. Then the sum from n equals 0 to infinity of a sub n squared is equal to L squared. Is that true or false? Well, this is false. And what's going on? Well, of course, the thing is that squaring does not work well with addition. If I square L, that's L squared. But if I square this other side, that doesn't mean I just square any individual terms. I have a lot of cross traffic. Now, if you're still not convinced, we should talk about what we mean when we say true and false in mathematics. So when we say true, what we mean when we say the word true, that's the word means always true. It's not just true most of the time. It's not just true some of the time. When we say true, it says no matter what a sub n you give to us, as long as it satisfies this relationship where you have the if, then it has to satisfy that conclusion where you have the then. False, now here you might say, okay, so false means always false? No, false means not true. And so in particular, that means at least once it fails. So if you can come up with even one scenario where it's not true, then it's false. So that's what we mean when we say true and false. So if you're not sure about whether something is true or false, try some examples and try some like really easy things that you know about. So things that you know about are things like geometric series or harmonic sum. Harmonic sum is a classic example because harmonic sum is always like right on the edge. So you can actually see it here. So for instance, what do we know? The sum from 1 to infinity of 1 over n, what is that sum? Do you remember what that equals? It's infinity, because it diverges. It's a harmonic series. It gets arbitrarily large. But the sum from n equals 1 to infinity of 1 over n squared, well, we don't know what it converges to. Actually, we do. It's pi squared over 6. We don't know it in our class, but it converges to something. We do know it converges because it's a p-series. It says infinity squared equal pi squared over 6. No, it doesn't. So that's why it's false, because there's at least one case where it's not true. But like I said, we don't have to justify these. But what you want to do is be able to get to the point where you're comfortable enough to think about the processes. So what we're trying to drive at is, do you understand series well enough that you're like, okay, I can adapt and I can figure out what's going on here. So part B suppose that the sum of negative 1 to the n a sub n diverges, and all the a sub n are greater than or equal to 0, then the original sum of a sub n diverges. So this is like I have an alternating series which is diverging, and it says, okay, the original series has to diverge. Is this true or false? It's a true statement. It's true. Now, I will tell you that we can be really sneaky, and if we took that part off, it's actually a false statement. So that shows you how sensitive some of these things are. And so the reason why you want all the a sub n to be greater than or equal to 0 is that what happens is when you add up just the a sub n, that says you're adding up positive things. If the sum of just a sub n were converging, then the fact that you had alternation doesn't do anything. It has to converge as well to be absolutely convergent. So this is sort of an idea of absolutely versus conditional. Okay, so that's true. Now, the last one. The sum n equals 0 to infinity of fn minus fn plus 1 is equal to 0. Well, let's just see. So that's f of 0 minus f of 1. So that's n equals 0, plus the next term, f of 1 minus f of 2, plus the next one, f of 2 minus f of 3, right? Because this is what happens. If you're not sure, just write down the first few terms, dot, 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 right? And the f of 1's cancel, the f of 2's cancel, the f of 3's cancel, so forth and so on. And it looks like this didn't cancel, and therefore the statement is false. Now, you might asking, what? You're messing with my mind. Well, the thing is, you have to be careful. Because it's false if this piece here, this little f of n, what happens to it? Because if you think about partial sums, this is why you have to be careful with telescoping sums. If the thing on the end is getting small, it would be true. So for many, many examples, this is a true statement. But if the thing on the end is not getting small, say it's getting close to 1, it won't converge. So we actually had this on a final exam a few years ago where we had the sum, I think it was n equals, well, let's say, we'll say 1 to infinity of cosine squared pi over n minus cosine squared pi over n plus 1. And it was something similar to this. And so when you see this and you work it out, you're like, oh, okay, well, it's something really simple. But the problem is that the fn term is not going to 0. And so if the fn term doesn't go to 0, what ends up happening, what's the true statement is you want to look at f0 minus fn, because what happens, the word telescoping means that the middle terms cancel. And let me use a capital Fn just to say, so this is if I only add up the first few n terms. And the question is, what happens to this as your capital N goes to infinity? That's what happens in a telescoping sum. Oftentimes we forget to account for that. So be a little bit careful. Don't take the true-false statements, just be like, oh, I'm going to just think about them, just true, false, true, false, true. No, that's not the pattern. Just apply a little bit of thought. They aren't meant to trick you. This one is definitely on the closer to the subtle edge, but we just want to let you be aware. This is the kind of thing that we want you to make sure you look out for. All right, now we'll get into we'll do some computations. That's what we signed up for Calc 2. We wanted to do computations. Find the integral of y squared over 4 minus y squared to the 3/2 power. So this is from the first part of the course, which is all about our integration techniques. How do we do certain integrals? And here, there's a big clue. The fact that we see a square root floating around, and we have something inside of our square root where something's being added or something's being subtracted. So when we have this situation going on, we say, aha, it's our old nemesis, the square root sign. And we've been figuring out how to get rid of the square roots. So this is indication of trig substitution. So we want to be ready for a trig substitution problem, including how to spell the word substitution. I feel like that cannot possibly be the right way to spell substitute. Okay, we'll call it trig sub. You got to be ready for a trig sub problem. All right, so we want to make sure we can handle that. So here's the key. How you think about trig substitution is you're using trig functions in such a way so that when you do your Pythagorean identities, you can get rid of your square roots. So, as examples, what can we do? Well, if we have our function, what's inside the square root is a squared minus u squared, then that says the right substitution to make is the sine function. If it's a squared plus u squared, the right substitution to make is the tangent function. And if it's u squared minus a squared, the right substitution to make is the secant function. And so the a just tells you what you need to scale by. So once you remember it's trig substitution and you can say, okay, it's either sine, tangent, or secant, you just sort of say, okay, which one should I go with? Now in our case, because it's 4 minus y squared, that's the a squared minus u squared. So our case says we want to make our substitution u equals 2 sine theta. Now if we, well, not u, y. Y equals 2 sine theta. So dy is 2 cosine theta d theta. So our integral becomes y squared 2 sine theta squared dy, so that's 2 cosine theta d theta. Divide that by, then we're going to have 4 minus 2 sine theta squared to the 3/2 power. Now, once you make your substitution, the next step is to say, okay, I now have a trig integral. And the way you work with the trig integral is you keep using trig identities, and you really want to simplify as much as possible. And we're going to have a couple of integrals that involve trigonometry by the time we get to the end today. So let's see, we have a 2 squared times another 2, so that's 8 upstairs times sine squared theta times cosine theta, and there's a d theta. Now downstairs, what do we have? Well, I can really think of the inside as I have 4 times 1 minus sine squared theta to the power of 3/2. And here's our first chance to use our trig knowledge. 1 minus sine squared. What's 1 minus sine squared? Yeah, cosine squared. Like, woo, nice. So, what do we have here? Well, we'll get 4 to the 3/2. Well, 4 to the 3/2, we think of it as square root of 4 cubed. So that's going to give us another 8 downstairs. I'll leave the upstairs alone for right now. And so what do we have downstairs? 4 to the 3/2, that's 8. And then we have cosine squared to the 3/2, which is cosine cubed. Well, the 8's cancel. I can cancel a single cosine upstairs and down. Now I have sine squared over cosine squared, which is tangent squared. Now, tangent squared is not on our short list of integrals that we can do, but it's really close to something that is on our short list of integrals we can do. It's really, yeah, close to secant squared. Yes, yes. So tangent squared becomes, what was it again? I'm sorry.
Secant squared theta minus 1.
Secant squared theta minus 1. Because tangent squared plus 1 equals secant squared. And now we have integrals that we can do. So we end up with integral of secant squared, tangent, and then minus theta. And because this is an indefinite integral, don't forget, plus c. Now we're not done, but we're close. So we got to say what is tangent of theta, and we have to say what is theta. So to finish, we go back to our original relationship. And we say, well, let's write this as sine of theta is y over 2. So I can come and draw a triangle. And in my triangle, I put theta in the corner. And I'll say sine is the opposite over the hypotenuse. Pythagorean theorem gives me my missing side. And you'll notice that the missing side isn't just any normal thing. It's the square root of 4 minus y squared. It's the same thing that motivated our original substitution. It's not a coincidence. It has to be. If it's not, something terrible has happened. So tangent of theta is the opposite over the adjacent. So we get theta over square root 4 minus y squared. Theta, well, I just need to get, there's a single theta here, I just have to get it out of sine. So theta is the inverse sine, or I prefer to write it as arc sine. So theta, whoops, why did I write theta here? Y, right, opposite, sorry about that. Minus arc sine, y over 2, and plus c, and now we're done. That's what we needed to get to. We needed to find the antiderivative. So the hard thing about trig substitution is always the how do you start. So make sure you think about what to plug in. And if you're not sure, you can always think back, okay, you got your trig identities, sine squared plus cosine squared equals 1, and our other trig identity, tangent squared plus 1 equals secant squared, and that can help guide you. All right. Let's find, again, another integral, x to the a, natural log of x dx. And here we're going to assume that a is bigger than negative 1. Now, looking at this, what's the right tool? Integration by parts. Parts. Now, what's the clue that you should do integration by parts? Well, essentially, when you have two functions multiplying together, that's a really solid clue, because integration by parts comes from the product rule, which is about multiplication. Another thing is you have a piece where you're like, oh, log of x, that part, I'm not so clear about how to find the integral, but derivative, I love it. So if you have something where it's like, okay, I know how to take the derivative very easily, but I don't know how to integrate, then that's a really good candidate for something where you use integration by parts. So remember, how does the rule go? It says integral of u dv, that's uv minus the integral of v du. There's a couple of different ways to write the notation, but this is one way to do it. So when you're looking at an integral like this, where you have integral of x to the a, natural log of x dx, what you have to decide is which part corresponds to the u and which part corresponds to the dv. The part that corresponds to the u should be the part where it's either something that you can't integrate or where taking derivative makes your life easier. Now in this case, I think there's a strong candidate for the u, which is ln of x. Right, because natural log of x, hard to integrate, but differentiation is beautiful. So u is natural log of x, and then dv is x to the a dx. du is 1 over x, so that's derivative of log, and then the integral of x to the a is 1 over a plus 1, x to the power a plus 1. So this becomes uv, so 1 over a plus 1, x to the a plus 1, natural log of x, minus the integral of v du. So 1 over a plus 1 times x to the a plus 1 times 1 over x dx. So if we clean this up, what we get is 1 over a plus 1, x to the power a plus 1, natural log of x. The 1 over a plus 1 can come out, and then we have the integral of x to the a. And we're like, hey, we just did the integral of x to the a. In fact, we did it right there. So what we'll get next is 1 over a plus 1, x to the a plus 1, natural log of x. So I'll have another a plus 1 coming down. So I'll now have two of them downstairs. So that's a plus 1 squared, x to the a plus 1. And because I want all the points, plus c. And then we're done. Because here, we don't have to go back to our original variable because we always stayed in our original variable. It's just a matter of applying the parts. Now, there are some things that can happen by parts. They may or may not happen on the exam. I will say that integration by parts is sort of like the new shiny thing that you get in Calc 2. Almost all the other integration techniques you learn in Calc 2 really have not very much to do with integration. So like trig substitution, it's just like, here's a sort of a wacky substitution. partial fractions, just like here's more algebra. Trigonometric functions, like here's how you use your trig identities. Integration by parts is like, here's something new. This is like really cool. So things to be aware of. You may have to do it multiple times. So that's okay. So that's all right to do integration by parts multiple times. What are some other things that you should look out for? Be ready to sort of like switch mindsets. So sometimes what you might do is you do an integration by parts once, and then like, okay, after you do integration by parts, you should always, this is a strange word because unfortunately it can be misinterpreted if I write it down. So the people who are just reading this won't understand what I mean by reevaluate. So when I'm talking about reevaluate, I'm not talking about like evaluation in a mathematical sense, but when I talk about reevaluate, it just says once you do one layer of integration by parts, actually take a look at the integral you have and say, suppose that I was just starting fresh, and I didn't know I was doing an integration by parts problem. How would I do it now? Because sometimes if you get stuck in that, like, okay, I can only do integration by parts on this, then you sort of stop yourself from seeing that, oh, there's something easy there right for me, because I'm not looking for it. So when I say reevaluate, every time that you do a step, take a look at the integral that you currently have in front of you and say, now what's the right thing for me to be doing? Now, number 4. Find the area inside the polar curve, r equals 2 plus sine theta minus cosine theta, shown below. So it's this shape right here. Now, you might be thinking, wow, Steve, if you just rotate it like this, it kind of looks like a heart. Because actually it is. It's a little bit like a cardioid. So not surprising that it does look a little bit like a heart. But, all right, so there we go. Now, how do you find area inside polar curves? So certainly, when you see something like area inside polar curve, so one of the things you want to get to by the time you hit the final is to be able to I can figure out how to recognize what the problem is asking me. I can look at it and say, I know what you're trying to get me to do, and I'm going to do it because I want my points. So this problem, it's very clear about what it's asking for. It says, hey, I'm asking you to give me something about area. So the basic formula is this. If I have some, say, set of curves, r equals f of theta, r equals g of theta, and I'm looking for the area between some set of angles, so from theta equals alpha to theta equals beta, this is usually how we describe our regions, then the way we do this is that our area is the integral from where you start to where you stop, so you need to know your bounds, and then there's a 1/2, and then it's the outer part squared minus the inner part squared, d theta. So that's your go-to formula. So it's 1/2 the outer minus the inner. Now normally there's no inner part. That's just if we're trying to really throw you off. So usually it's just 1/2 where it's just the outer part squared. So this is the formula. So once you know what the formula is, it's not so bad. A lot of this just goes, once you set it up, then you just follow through. So a couple things to be aware of. Don't forget the 1/2. That's important. And the bounds, well, they might be given to you, and they might not. If no bounds are given, you have to figure it out. So the way you find bounds is oftentimes you say, where do you intersect? You might have two polar curves. You say, where do these two curves intersect? That's usually how you find the bounds. But again, the bounds might be given to you. Do not stress about the bounds. If we do not give you the bounds will be super obvious. And if we do give you a problem in polar, we'll even throw in a picture. Not because it's important, because I like drawing pictures in polar. It's like, it was really exciting. I figured out, I learned how to do this like 2 years ago. And it's like, cool, now all the problems with polar get pictures because it's fun to do it. All right, so again, don't stress about that too much. All right, so once you have the setup, the problem is easy. So there's our setup, so we'll just write it down. So in our case, what are our bounds going to be? Can you see it? Yeah, we're going to go start at theta equals 0, and then we're going to swing all the way around until we come back to 2 pi, because our shape, really covers the full revolution out from the center, because the center is where you think of things in polar. Then you have 1/2, and then here there's no inside part. What you do is you go out to your curve. So it's 1/2 of your function, which is 2 plus sine theta minus cosine theta squared. All right. Well, that's going to be what? 0 to 2 pi. So you've got to square this out. Now, if you're squaring that out, this is maybe a little bit more challenging than most, but not too bad. Really what it means is you're multiplying everything in every possible pair. So it's like foiling with like a few extra terms, where the idea of foiling is every piece in here gets matched with every piece in there in every possible way. But because there's more pieces than just 2 in the first and 2 in the second, there's going to be more combinations. So instead of like foiling, it's like, because there's like nine things that have to go on. That's not a real word, by the way. It's just to remember the philosophy. So what do you get? Well, you get the 2 times 2, which is going to be 4. Then you're going to get a 2 sine theta, but you'll get another 2 sine theta, so that'll be 4 sine theta. Then you get a minus 2 cosine theta, and again you'll get another minus 2 cosine theta, so that's minus 4 cosine theta. Now we'll go to the next term, sine squared. Well, we've got power reduction we can use there. Then there's a minus sine theta cosine theta, but another minus sine theta cosine theta, so that's minus 2 sine theta cosine theta. And then come to the end, will be plus cosine squared theta. So that's our integral that we have to do. Now the good news is a lot of these pieces aren't very bad. For instance, notice we have sine squared and we have cosine squared, which if you put them together, their powers combined are 1. Then there's a 4. So that means that we have integral 0 to 2 pi of 1/2 5. The 4 sine theta, I'm good with that. I'm ready to integrate that. The 4 cosine theta, I can integrate that. 2 sine theta cosine theta, what can we do with that? Sine 2 theta. Yeah, one of our trig identities, There aren't very many, but the ones that we have, we should know. So we're ready to integrate. So 1/2 times 5, that makes that 5/2 theta. Then 1/2 times 4 is 2, and then integral of sine is negative cosine, so minus 2 cosine theta. Then we have 1/2 times 4 is 2, it's negative 2. Integral of cosine is sine, so minus 2 sine theta. Integral of sine 2 theta will be cosine 2 theta over 2. There's already an over 2, so that gets us to minus 1/4 cosine of 2 theta. And we're going to evaluate all of that from 0 up to 2 pi. So if you plug in 2 pi, you'll get 5/2 times 2 pi, which is 5 pi. Okay? That's all right. Minus 2 times cosine of 2 pi. Well, that's cosine of 2 pi is 1, so minus 2. Sine of 2 pi, 0. Then we have cosine of 4 pi. Well, cosine of 4 pi is 1, so minus 1/4. Subtract, plug in 0. We'll get 0. Then minus 2. Sine of 0 is 0. And cosine of 0 is 1, so minus 1/4. And the nice thing is that the minus 2's cancel, the minus 1/4's cancel. So our final answer is 5 pi. So that's kind of a nice answer. So yeah, so be prepared for polar integrals, and probably something you should look out for is make sure you're good with your trig identities. Because polar integration, oftentimes you express things in terms of your trig functions, and then you start squaring stuff. As soon as you start squaring stuff, now all of a sudden you got to be like, okay, I've got to handle trig functions where I start having higher powers. So do you remember what your basic trig functions, your trig identities? What are they? Do you remember? Sorry, excuse me. Do you remember all 6? Sine squared plus cosine squared equals 1. That one, people, they know it so well they don't even really think about it as a trig identity. Tangent squared plus 1 equals secant squared. Then you have your the one we used here, the double angle, sine 2 theta equals 2 sine theta cosine theta. Cosine 2 theta equals cosine squared theta minus sine squared theta. And then you get your last two, which are power reduction. So cosine squared theta is 1 plus cosine of 2 theta over 2. And sine squared of theta is 1 minus cosine of 2 theta over 2. So those are your 6 trig identities. So when it comes to trigonometric functions and manipulation, that's it. If you know those 6 and you can use them, you're going to be able to manipulate any trig functions that you work with to the point where it's something you can do. So that. On the other hand, if you don't know those 6, well, it's not so long. You can rederive most of these in just about 10, 15 minutes. But that's not how you want to be spending your Calc 3 exam. Calc 2 exam. You want to spend your Calc 2 exam having fun, just smiling at the professor saying, I know I'm going to do awesome on this exam. Find the volume when the region 0 less than or equal to y less than or equal to sine squared x for 0 less than or equal to x less than or equal to pi is spun about the y-axis. So our shape here, we have sine squared x, which does something vaguely sine x like. So let's say this is sine squared x. It's not a perfect drawing, but close enough, and goes from 0 to pi. And it's not so much that the drawing in particular is important. We just want to get some intuition about what's going on. Now, we want to spin this about the y-axis. So the y-axis, that's this axis over here. So we're spinning it this way. So what I like to do is I like to think about, all right, there's 2 different methods when we talk about spinning and volume. Odds are pretty good we're going to do at least 2 volume problems by the end of today. So let's figure out which one this is. I'd want to integrate this in as an integral with respect to x. And the reason I want to stay with x is I don't think if I solve x as a function of y, it's going to be a very nice looking function. In fact, it looks like it's going to be a very unpleasant function. So I'm going to think about there being a little tiny slice here. And then I think about how does that slice, what happens to it? And the answer is, if I spin that slice around, I form this shape. So that small slice is swinging out what looks like a little tiny cylinder, but of course we don't call it a cylinder, we call it a shell. So this is a problem that involves the shell method. So we need to know what's the shell method. So the shell method says the following, that the volume is equal to the 2 pi integral a to b of, there's 2 pieces. There's the radius and there's the height. And then there's this little last piece which I'll call width. And I'll explain what these pieces translate into. Now when we're integrating with respect to x, our width is our dx. It's our little tiny width. Our height is usually our function, f of x. Now if it's between 2 curves, it's the top curve minus the bottom curve. But most of the time when we spin regions, it's just from f of x down to the axis. So it's f of x. Our radius is how far are we from where we're spinning around. So we're spinning around the y-axis. So the question is, how far is this away? And the answer is, it's x. So our formula is 2 pi integral 0 to pi of x, because a and b are where we start and stop. Our height is sine squared of x and dx. All right, so that's the integral that we have to do. All right, well, let's piece things together, and hopefully we should not take too long because we have many problems, and at the rate we're going, not enough time. So we'll have to speed things up. All right. Now, let's talk about how we find this. So, can we integrate this? That's a little bit hard. We have parts, but let me point out to you this thing. What should we do with sine squared? Power reduction. So, this is going to be 2 pi integral 0 to pi, And power reduction says this will be x, it'll be 1/2 minus 1/2 cosine 2x. And I can actually separate this into two integrals. So this is 2 pi integral 0 to pi of 1/2 x. And then the other integral, and I realize I probably should multiply the 2 by 1/2 at the start, so I'll do that for the second integral, minus pi integral 0 to pi of x cosine of 2x dx. All right. Now the first integral we can do, there's not much thought that has to go into this one. So this is pi times 1/2 x squared from 0 to pi, which means that we're going to end up with 1/2 pi cubed. So that's the first integral. No big surprises there. And the second one isn't a very big surprise either, because we've already said it. It's going to be integration by parts. And the thing that makes it integration by parts is I have sort of two things coming together. And here we can say, okay, what should be the part that we take a derivative of? In other words, what's the u? Can we see it? Well, the u should be x. Now, why should that be the u? Well, because when we take the derivative of that, it becomes simpler. It becomes 1. If you integrate cosine, you get essentially sine. But if you take a derivative of cosine, you get essentially sine. So it doesn't really matter what you do to that. So what you want to say is, well, let me figure out what to do to the other one to make things easier. So we want to take the derivative of the other part. So that's going to be u, du equals dx. Here, we'll let dv equal cosine of 2x dx. So we get that v, the integral of cosine 2x dx is 1/2 sine of 2x. So what do we have? We have that 1/2 pi cubed from the front. We won't forget about that. Minus pi. And then we'll have times uv. So 1/2 x sine of 2x. And then you evaluate from 0 to pi. It's a definite integral. Minus the integral of v du. So 1/2 sine of 2x dx from 0 to pi. Now, the nice thing is when you plug in 0 and pi to this piece, when you plug in 0, you get 0. When you plug in pi, because of that sine of 2 pi, you still get 0. So this part goes to 0, which is nice. So you get your 1/2 pi cubed. Minus makes a plus. You get a pi. The integral of 1/2 sine of 2x. Well, the integral of sine is negative cosine. So there's actually a negative. I'm going to now take it to 1/4 and the cosine 2x. Now, why a fourth? There already was a half, and then I have to divide by 2 again. Evaluate that from 0 to pi. Well, what's going to happen? Well, when you evaluate here, what you're going to get is, if you ignore the negative 1/4, just plug in here. Cosine 2 pi is 1. Cosine 0 is 1. Oh, well, it means that you get cancellation. So that this part also is 0. So what we end up with is that we end up with simply 1/2 pi cubed. And that's okay. But we have to check, we have to do the work. So 1/2 pi cubed. And that's our answer. And life is good. All right. Seems almost too good. Well, should we really look a gift horse in the mouth? Now I'm nervous. Have I made a mistake? No, it looks right to me. Does it look right to you? We'll stick with it. We'll stick with it. Let's move on. We have other things to do. All right. Find f to the 20th at 1, where f of x equals x squared over x squared minus 2x. So at the first glance, when you see this, is like, this is not a Calc 2 problem. This is a Calc 1 problem. Because all you have to do, just take 20 derivatives, and then you're done. Now, you should, of course, not take 20 derivatives to do this problem, because first off, you would probably be wrong by the time you hit the fourth derivative, and second off, you don't have 20 hours to write down the derivatives. So you want to do things in a faster way. So this is an application here. So whenever you're talking about high-order derivatives, the place where we saw high-order derivatives showing up in Calc 2 was at the very end. And that was with Taylor series. So remember, what do Taylor series look like? Well, suppose I have f of x, and it's equal to a summation, k equals 0 to infinity, and it looks like the following. The kth derivative evaluated at a over k factorial x minus a to the kth power. This is the Taylor polynomial centered at x equals a. So what's going on here is the following. It says, hey, I store derivatives in Taylor series. So if I have a Taylor series, then that tells me I have all the high-order derivatives. All of them, not just some of them, all the way through infinity. So what we're really going to do here is we're going to say, okay, we're going to figure out what the right Taylor series for this is, and then we're going to grab the right term in the Taylor series. Now, we're after the 20th derivative. So what's happening here is if we think of it, and notice here we have 1, so this is at a equals 1. What we're going to have is we have a bunch of terms, then we're going to have a 20th derivative at 1 over 20 factorial x minus 1 to the 20th, dot, dot, dot. So I want to know what is in front of x minus 1 to the 20th. If I know what's in front of x minus 1 to the 20th, that tells me about my 20th derivative. Okay, so how do we do that? Well, we start thinking about what Taylor series do we know? And that really match with what this does. And well, it's not e to the x, it's not cosine x, it's not sine of x, so it looks an awful lot like geometric. And I would say it's one of the big ideas from this class is geometric series. Now, you're probably thinking it doesn't look very geometric right now. Well, we'll get to that. We'll get to that. Now, when it's geometric, that says I want to write this as 1 over 1 minus z. Because if I can, that's the sum, 0 to infinity, of z to the k. For now, let's not worry about the x squared. We'll deal with the x squared in a second. So I'm going to think of the x squared. It's a polynomial. Polynomials are easy to deal with. I'm going to focus on the bottom. Now my goal, because I'm centered at 1, I want to write x squared minus 2x in terms of things that look like x minus 1. And I think to myself, x squared minus 2x, and then I hear the word x minus 1, I'm like, you know, they're really close to each other in the following sense. If I were to take x squared minus 2x and to add 1, this would be x minus 1 squared. But can I just add 1? Well, if we subtract 1, then yes, we can. And now, you'll see what do we have? We have 1 over x minus 1 squared minus 1. Well, I want to make it so it's actually the other order, so this is x squared. And then I have 1 over, and I'll pull a negative out, 1 minus x minus 1 squared. So I pulled the negative out of the denominator and put it in front. Now, it's of the right form. See, because what's happening here is you should really think of this z as a box. And then I just say, look, whatever is in that box, that goes right there. So our box, we've put into it x minus 1 squared. So what goes out, well, this is negative x squared, and then it's going to be the summation, k equals 0 to infinity, of x minus 1 squared to the kth power. So that's negative x squared times the sum k equals 0 to infinity of x minus 1 to the power 2k. And now you're like, haha, we're basically done. Well, one little catch, that x squared. So how do we fix our one little catch? There's a couple ways to do it, and I'll do an example over here. So I will say that we've essentially done the key idea, which is just to highlight what goes on here. What we're about to do, if you're like, I don't like that, Steve, be like, that's okay. we'll probably give you something different on the exam. And that we would definitely give you something different. The review problems, these are the ones where I have fun. Okay, so I think of myself x squared. Well, I want to make it written in terms of things that look like x minus 1. So I'll say, well, it's kind of like x minus 1 squared, right? Well, not quite. What does x minus 1 squared look like? It looks like x squared minus 2x plus 1. Okay, so now I say I want to cancel out the minus 2x plus 1. So I could add 2 times x minus 1. And if I did that, I'd really be adding 2x minus 2, which brings me up to what? Well, the minus 2x's would cancel, and that would get me up to x squared minus 1. Well, I like the x squared, I just don't like the minus 1, so I just add 1. So what I can do is I can rewrite x squared in terms of x minus 1. So if we do that, we get that this expression, sorry, I just want a little bit of space here, is equal to x minus 1 squared, and I'll put a minus out here in front, times the summation k equals 0 to infinity, x minus 1 to the 2k, and then minus 2, x minus 1, the summation k equals 0 to infinity of x minus 1 to the 2k, plus, that's darn minus. I keep forgetting about minus, summation k equals 0 to infinity of x minus 1 to the power 2k. And you can move the x minus 1 squares in. So we have minus the summation k equals 0 to infinity of x minus 1 to the power 2k plus 2. Then minus 2, summation k equals 0 to infinity of x minus 1 to the power 2k plus 1. And then minus the summation k equals 0 to infinity of x minus 1 to the power 2k. Now, remember, what am I after? X minus 1 to the 20th. So let's look in each piece and ask what happens. Here, is it possible for me to get x minus 1 to the 20th? It is. When does it happen? K equals 10. So this thing has some various terms, and then at k equals 10 I get a minus x minus 1 to the 20th. And then there's other stuff. In this middle term, can I get x minus 1 to the 20th? No. So it's just going to be dot, dot, dot. Because it's not going to have anything that's relevant. Can I get x minus 1 to the 20th here? Yes. At k equals 9. And what I care about is the coefficient. Again, it's another negative. Now, oftentimes, I will tell you that you get something in front. So it's a little bit more exciting. So you get a minus x minus 1 to the 20th when k equals 9, and then you get other stuff here. And so we say, aha, if we put this all together, what we see is that, lo and behold, we get minus 2 times x minus 1 to the 20th when we write this as a Taylor series. Now, why is that important? This part right here, this minus 2, has to match that part. So, that tells us that the 20th derivative evaluated at 1 over 20 factorial has to be equal to negative 2. So the 20th derivative at 1 has to equal negative 2 times 20 factorial. That's the answer. Now, it did take up a page, but that's a lot less than if we actually tried to take 20 derivatives. I promise you, by the time we'd hit the third or fourth derivative from here, we really would have said, let's just start rederiving calculus from scratch and figure out a better way to do it. Okay. All right, that was probably the long one. The rest of them, they'll all be quick and easy, right? Right? Hopefully. All right. One of our favorite types of problems. You can already see it. Do not evaluate. We love those problems. Okay, so set up but do not evaluate integrals which find the surface area when y equals log of x squared plus 1 for 0 less than or equal to x less than or equal to 1 is spun around the x-axis and around the y-axis. Now, it doesn't say it, but I'll go ahead and tell you that because log of x squared plus 1, the inside is always at least as large as 1. So log of x squared plus 1 is always positive, or at least greater than or equal to 0. It starts at 0 here, and it moves up in some way. So here's our curve. This is y equals natural log of x squared plus 1, and we're going between 0 and 1. Now what we need to do is to set up the integral. So this question here is testing, do we know surface area? Now surface area, there's a generic formula, and once you know the generic formula, it's actually pretty straightforward. So it's going to be the integral from where you start to where you stop. There's a 2 pi, and then there's a radius, and then there's a length. Now, when we talk about radius, that's to where you spin around. When you talk about length, this is specifically arc length. In other words, a little piece of the curve, which for our purposes, it's the square root of 1 plus f prime of x squared dx. So that's what is referred to as length. So this is, of course, when you have y as a function of x, you can transform it to x as a function of y, and then you get like g prime of y dy. So let's do part A. Well, the integral from a to b, that's the integral from 0 to 1, 2 pi. And the big thing that happens between these two is just understanding the radius. So part A, we're doing the x-axis. So the idea is we're just taking a little piece of the curve. So the radius is how far are you from the x-axis. So this would be f of x. So the radius is f of x, which in our case, is natural log of x squared plus 1. So it's our function. This is our f of x here. And then we have the square root of 1 plus, now you take the derivative of log of x squared plus 1. Well, it's 1 over x squared plus 1. And then you times it by the derivative of the inside, which is 2x on the top, and you square it. Now from here, you're done with part A. Because this is a setup problem. This is not a setup and evaluate. It's just a setup. So we've been set up. So we go to part B. So part B, the y-axis. So for the y-axis, we're asking, how far am I from the y-axis? That's the y-axis. And the answer is, my distance, the radius of where I'm spinning to, is x. So it's still same bounds, 0 to 1, still the 2 pi, but now the radius, instead of being the function, is x. The other part doesn't change. It's still the 1 plus the f prime of x, 2x over x squared plus 1, quantity squared dx. So this problem is almost purely a, do you understand how to set up surface area? And I think there's sort of two hard parts about this. The first hard part is, do you remember the basic formula? And after you remember the basic formula, the second hard part becomes, do you remember how to interpret the radius? Because your interpretation of radius changes depending upon like which axis you spin around. And sometimes you don't even spin around an axis. Sometimes you might spin around like the line y equals 5 or something. So once you understand how to figure out your radius and you know the formula, these types of problems are fun. It's hard to find integrals you can actually do though. So a lot of these are set them up. Number 8. Find the volume from the solid resulting from the region 0 less than or equal to y less than or equal to secant cubed of x for 0 less than or equal to x less than or equal to pi over 4 being spun around the x-axis. So we have this region, secant cubed of x. I don't know exactly what it looks like, but secant of 0 is 1, and it's going up. So it's going up. Let's say it looks like this. Here's pi over 4. So here's my basic region. And we are spinning this around the x-axis. So when you're doing a volume of revolutions, you got to pay attention to which axis, because it really significantly changes the technique you're going to do. So if we're spinning here around the x-axis, again, because I'm given y as a function of x, unless I have a strong reason, I'm going to stay with x. So I draw a little tiny sliver, and I spin it according to the instructions. So in this case, I spin it around. And as I spin it, I'm going to form a particular shape. And that shape is going to help guide what method I use. So what shape do I form? Disk. So disk is the right method. Now, you might have a shape within a shape, which would become a washer, but oftentimes we just start with the disk. Essentially, a washer is a disk minus a smaller disk. So let's know the formula. So the volume is the integral start to stop. You have pi, then you have the radius squared, and then you have your width. Because what you can think of this is you can really think of it as like a really tiny, very short cylinder. So when I say short, that's the width. And so if you think of a cylinder, it's pi r squared. It's the big circle times the width of that cylinder. So this width is usually dx or dy. The radius is the distance from the top of the curve to where you spin around. So most of the time, it's just the function f of x. So this is the generic formula. Of course, you can modify this depending upon, okay, are we spinning around a different line? And once you understand when you're spinning around a different line, you say, okay, I just adjust the radius in the appropriate way. So let's see what this becomes. So our integral is going to be from 0 to pi over 4, and that comes from these bounds. The bounds have to be given. You can't really, well, maybe you have to find the intersection of curves, but almost always they give the bounds. And then we have pi, and then we have secant cubed of x squared dx. All right, so that's it. That's our integral. So we have to integrate 0 to pi over 4, and so that's pi secant to the 6. Well, how do we integrate something like secant to the 6? Well, it's not on our list, but this is one of those trig integrals, right? Now, if you have integrals involving secants and tangents, your ideal situation is either have a secant squared at the end and everything in terms of tangent, or have a secant tangent on the end, everything in terms of secant. Which one of those two situations do we seem like we're heading towards? Yeah, if we have a secant square on the end, I think we have a good shot. We already have a lot of secants here. So in particular, let's write this in the following way. I'm going to pull off a secant squared at the end. And then I'm going to write secant to the 4th, because that's what's left. I'm going to think of that as secant squared squared. Now, why secant squared squared? Why not secant to the 4th? Well, secant squared, we have a nice formula for. What does secant squared become? It becomes tangent squared plus 1. And there's a square in there. There's lots of squares. This is very squarey, this problem. Now we're ready for our substitution. We can let u equal tangent of x. Du becomes secant squared of x. And dx. And lo and behold, after we make that substitution, we're going to have an integral which is not so bad. Now, our current bounds are from 0 to pi over 4. We substitute tangent of x. Where do our new bounds go from? 0 to 1, because tangent of pi over 4 is 1. Then we have a pi. Then we get u squared plus 1 squared du. Now, at this point, you're probably thinking, okay, maybe if I do a trig substitution, maybe u equals tangent or something. No, no, no. How do you integrate this? You square it. Yeah. See, this is a nice whole power. There's, just because we know lots of really fancy, powerful tools doesn't mean that the basic tools aren't any good anymore. In fact, the basic tools are often the best. Indeed, the people who are really good at calculus aren't necessarily the people who know the most facts about calculus. It's the people who can use the basic tools the best. And the more you have your basics down, the better off you'll be. So we get a pi. Integral of u to the 4th is 1/5 u to the 5th. Then 2u squared is 2/3 u cubed, and then 1 becomes u. and we evaluate from 0 to 1. And the nice thing is you plug in 0, you get 0. When you plug in 1, you get pi, a fifth, plus 2/3, plus 1. Now, if you were in the mood and said, I want to simplify, which is a very dangerous thing to say, but maybe you do, you can put everything over 15. And if you do that, apparently you're going to end up with 28 over 15 times pi. All right. And there's the answer. Okay, cool. Now, in case you're wondering, do you have to simplify? The answer is no, unless it explicitly states you have to. You might want to, just because you have time and you like things to look nice. Your graders might appreciate that. I will tell you, I did a substantial amount of grading last night, and I was amazed at how many people had difficulty of adding numbers. Things like 26 and 4. They were not able to add those together, you know. I just hope that was because the test was a little bit later than usual for that particular exam. I don't know, but who knows? Who knows? Be careful. Check your work. Check your work. So, number 9. A storage tank has the shape of an upside-down cone, which is 6 feet across at the base and 6 feet high. Now, normally we would give a picture, so here's the picture. It's a cone, but I'm calling this one upside down. Now, some people might say this is right side up. Maybe I should have said pointy side up. Then it would have been unambiguous. Like, oh yeah, pointy side, yes. All right. So, but certainly when we see, oh, it's 6 feet across here at the base, and it's 6 feet high. Now, the tank is currently full of a liquid which has a density of 50 pounds per cubic foot. Well, all right. So here's our liquid. That's dense-ish. And it's being emptied by being pumped out to a point 4 feet above the tip of the cone. So I can see I did not plan well, but let's say up here we need to get to an additional 4 feet. Determine the total work done in emptying the tank. All right, so essentially we have to think about what is work. Now, the basic answer is that work equals force times distance. And oftentimes when we think about force, we're going to think about this in terms of pounds, and distance we're going to talk about in terms of feet. So we're looking for foot-pounds. Now, we're going to do another type of work problem later on. So I'm going to focus on this particular type of pumping problem. So we're going to come back and talk more about work later on. So let's talk specifically in this scenario. What's going to happen here is what you should think of happening is that you're just grabbing a small, thin piece, such as this part right here, and I'm going to say, I'm going to pump out that part right there and say, what's that amount of work? And then once I've had that amount of work figured out, I'm going to add up for all the small, thin parts. I get the total amount of work, and life is good. So we come to sort of our first decision. And in some sense, it's almost the only decision that we get to make for problems of this type. But these decisions are important. And that decision is, what do we do with our coordinate system? So oftentimes when problems involving work are given to you, there is not a built-in coordinate system. So that means that a choice has to be made. And when we talk about coordinates, what we're saying is, where is 0? Which way is a positive direction? Because you have those two choices. You can say, I can set 0 anywhere I want. So for example, I could put 0 at the very bottom of this cone, at the tip of the cone, or I even could set 0 up here at where it's being pumped out. It's our choice. And then I could orient things so that increasing was going up, or I could orient so that increasing meant going down. Now, it will not change the final answer. That's the good news. It might change how hard it is to get to the final answer. That's the bad news. And so you do want to not neglect this. Oftentimes I think that, when I say don't put 0 in the middle of the cone. That's like silly. Come on. There's obvious candidates. Usually if you pick an obvious candidate, it's pretty good. So like the top or the bottom. And for me, because I see that I have essentially a triangle going on here, I want to put 0 right there at the top. And I'm going to put it so that as I orient, that's going down. All right? It's a choice I make. I'm allowed to make that choice. It's a free I don't want to say it's a free country, you know. Physics, you know, you get choices. It's a free physics. Well, that doesn't make any sense. All right. You have choices. You have choices. Okay, now the rest of this is essentially forced onto you. So you're going to break work up into little pieces. So whenever you break things into little pieces, that means you're integrating. Integration is about breaking things into little parts. You have where you start and where you stop. So the philosophy of integration, I hope by the time you've hit this part of Calc 2, you've come to this understanding, is that the philosophy of integration says take what you're looking for, break into small parts, and then add the parts together, and that gives you what your total is. Now, we're trying to find work. So we're really trying to think about work as little pieces of work. So there's a distance, which is how high you move whatever you're pumping to. And then we got to get the force, which is the pounds. Now, in this type of scenario, well, we need to get a weight of this. So what we need is we need to know how much weight is in there, which means that we need to know the density times the volume. And the volume is the area of a cross-section. I should have probably planned better here. Area of a cross-section, and then the height of the cross-section. So those are the pieces of work. So if you take the height times the area, so the area is like the circle you see here. The height is the little tiny thickness. That's the volume of a piece. The density times the volume gives me the weight of the piece. Then the distance times how heavy that piece is gives me the work done to move that out. So that's how it all fits together. When you understand how things fit together, it's really easy to remember the formula. If you just take it as a formula, it's super easy to forget parts of it. So let's go through each piece. Some of them are really easy. The height, let's call our variable y. So this is dy. The density is almost always fixed. That's 50. So here, I'm currently at y. I want to go all the way to 0 and then an additional 4. So the distance I have to move is essentially from y equals negative 4 to the current value of y. So our distance would be y plus 4. Our bounds, well, we can think about starting from the tip and going down to the very bottom, so 0 up to 6. Which means that we get to the area of the cross-section. All right, so how do you do area of a cross-section? Well, you say, what's my cross-section look like? It's a circle. So that's going to be pi times a radius squared. So I just have to figure out what my radius is. So to figure out my radius, here's where I talked about it looks like a triangle. If I slice down, what do I see? Well, in my slice, I'll see a triangle, a big triangle that looks like 6 here. It's 6 high. But I want to say, what if I just go down by y? How far across am I? Well, I hope you can see the answer without too much work. Can you see what it is? Yeah, it's y. And I even resisted the urge to answer, well, we need to know. See, that's how serious I'm treating this exam. I'm even losing the ability to joke. So, all right. Now, if you can't see that right away, think about ratios. So let's call this, for a second, r. And what you can say is, well, the ratio of r as to y, so this length to that length, is the same as this corresponding side, 6, is to the corresponding height, 6. So you get that y equals r. So, and that, by the way, we benefited by our choice of where we put 0. If we had put 0 at the bottom, it would not be such a clean expression. So this becomes y squared. So now we have a beautiful integral. So it becomes 50 pi, and then we get y squared times y plus 4. That's y cubed plus 4y squared from 0 up to 6 dy. So 50 pi times 1/4 y to the 4th plus 4/3 y cubed from 0 up to 6. And if you plug in 0, you get 0. So you get 50 pi times 1/4, 6 to the 4th, plus 4/3, 6 to the 3rd. And we're perfectly happy not simplifying. Have I forgotten something?
Yeah, why is the radius not half y?
Why is the radius not half y? Excellent point. Y is the diameter. So we'll fix that. Y over 2. If we square that, that becomes, see, good. Thank you for pointing that out. Phew. All right. Well, I get to drop a problem, right? All right. Now, it didn't ask us. Sometimes these problems do ask us, what are the units? Yeah, foot-pounds. Or pounds feet. Usually, most physicists say foot-pounds. And there you go. That's the amount of work. All right. Ooh, we're getting into our series part. Now we're getting serious. All right. For A and B positive, show the following sum converges and find its value. So I have the sum n equals 0 to infinity, a to the n plus b to the n over a plus b to the n. And it says simplify your answer for the value as much as possible. So that means hopefully it has a really nice answer. Now when I see this, I say, okay, I'm actually going to have to find the value for the sum. If I'm looking for the value of the sum, there's only 3 things I can do, which is geometric, telescoping, or it's a Taylor series. Now that's if I wasn't taking a final exam. I'm taking a final exam. How many things can I do? I can do 2. I can do geometric, and I can do, it's a Taylor series. And you're probably thinking, wait a second, Steve, why did you take telescoping out? It didn't make the cut of topics. And I know you're thinking, oh man, I love telescoping. It's okay, we'll challenge you enough with other things. All right, so in this particular case, what are we thinking? What does it look like?
Geometric.
It's geometric. What's the clue? Well, the clue is that you have these as exponents. So you have something to the nth power. And so when you see numbers to the nth power, A and B are numbers. We don't know what they are. Right now we're just told that they're any positive numbers. Whenever we see something to the nth power, then that tells us that, lo and behold, that's really a geometric type thing. Now, the thing for geometric that we need to remember is that if we take the sum of r to the k equals 0 to infinity, this is 1 over 1 minus r. If the number r is small. That's all we need. As long as r is small, that's a true statement. So, let's look at this. One thing we can do is we can say, well, this is the sum, n equals 0 to infinity. Let's just think of this as 2 pieces, a to the n over a plus b to the n, and b to the n over a plus b to the n. Because we are allowed to break up addition in the numerator. That's one of the nice things about upstairs, is that you're allowed to break things apart. Downstairs, you're not. That's why addition downstairs, what a pain. But upstairs is like, woohoo, life is good. And in particular, we say, okay, this looks like the sum from 0 to infinity of a over a plus b to the nth power plus b over a plus b to the nth power. So it really does look a lot like a geometric sum. And now we come to the question that says, all right, let's just think of these individually for just a second. Because what we want to do is we want to break this up. We want to write this as sum n equals 0 to infinity of a over a plus b to the n plus the sum n equals 0 to infinity of b over a plus b to the n. And we will. And we will do this. But remember, they said show it converges. So how do you show it converges? And the answer is you just have to do your check. Is what you're doing to a power, is it small? Because if it's not small, the formula is bogus. It just doesn't work. And I mean, it's a formula, but it's just untrue. We don't want things that are untrue. So we look at a over a plus b. And the question is, a over a plus b, what's true about that? Well, what's true is everything is positive. Well, if I make the numerator a little bit bigger, I only make the value bigger. So first off, since everything is positive, it's certainly bigger than 0. And it's less than a plus b over a plus b, also known as 1. So that tells me that a divided by a plus b is going to be smaller than 1 in size. How about b over a plus b? It's the same reasoning. I can say, okay, it's smaller than a plus b over a plus b, which is 1. So both of these pieces here, this a over a plus b and this b over a plus b, both of them are smaller than 1. And therefore, the geometric series, no problems, we can find the geometric series. So we get this as 1 over 1 minus a over a plus b plus 1 over 1 minus b over a plus b. And if it weren't for that simplify as much as possible comment, we'd actually be done. But we do have to simplify as much as possible. So what are some things we can do now?
Multiply the bottom by a plus b.
Yeah, multiply everything by a plus b. Top and bottom on both equations. So if you did that, you would get a plus b over a plus b minus a plus a plus b over a plus b minus b. All right, well, we almost made it. You can see that we get a little bit of cancellation. The a's cancel. That's good news for us. B's cancel. More good news for us. Now we say, well, let's add these together. So the first denominator, it's b. Second, it's a. So common denominator would be ab. So we get a times a plus b times a plus b all over a times b. And the top, do you see what we can write that as? Well, you can factor an a plus b out, and if you factor an a plus b out, what's left? Still a plus b, so it's like a plus b squared over a times b. And that, I don't think we can get simpler than that. So there's the sum. So regardless of what choice of a and b, as long as both of them are positive, that's going to be what it reduces to at the end. All right. So geometric series are actually really fun. If you see something like this, geometric series, life is good. Now, you should know how to sum a geometric series. In general, let's just do a little comment here, because geometric series are really important. If you have a geometric series, so it always looks like a term plus then you multiply by r. And by the way, the reason we call it geometric is the idea of multiplication. So there's two things. There's arithmetic, that means you add the same thing each time, and geometric means you multiply by the same thing each time. So geometric is about multiplication. So if you ever have a geometric series, a plus a times r plus ar squared plus ar cubed, and you keep going, the value of the sum is equal to a over 1 minus r. So keep track of things. It is possible that the first term might not be 1. We get so used to having the first term be 1 that we forget, well, it doesn't always have to be 1. So if you are dealing with a geometric sum, just say, okay, what's the first term in my sum? What am I multiplying by at each time? And then you're good to go. So just in case, keep that in mind. May or may not be relevant. I just like throwing out useful facts. And sometimes, occasionally, they are useful on the final. And sometimes they're just useful for life. You're like, well, you know, you're a few years down the road, doing some homework with your kids. Like, I love geometric series. Let me tell you more. Determine if the following sum converges or diverges. Justify your answer, including the names of any test used. So we have this crazy looking sum. It does look crazy looking to me. And it looks like it's going to be hard for us to figure out whether this sum converges or diverges. So we start looking at this sum and we start thinking through what tests do we have. And the answer is there aren't that many tests left to us because we've thrown out quite a substantial amount. But even if we hadn't thrown out very much, I claim that there's one test that you should be drawn to. Root test. And the reason you should be drawn to the root test is because everything is raised to the nth power. If everything is raised to the nth power, then what you should do is take the nth root. So the root test says what? Well, we're going to apply it, and as we go through, we'll talk about what it says. We're going to take the limit as n goes to infinity. These are nice positive pieces, so no problem about negative signs, of our individual piece, not the sum, just the individual terms. 2 to the n squared plus e to the n plus 17 over log of n plus 5n plus 3n squared to the nth term. That's our original term, and then we're taking the nth root of that. So this becomes the limit as n goes to infinity of 2n squared plus e to the minus n plus 17 divided by log of n plus 5n plus 3n squared. Now at this point, we trust you enough that you know how to take these types of limits. And for these types of limits, you look at the highest growing terms. What's the highest growing term on the top? The 2n squared. Highest growing term in the denominator? 3n squared. So you take 2n squared over 3n squared, where does that go to? 2/3. So this limit is 2/3. We will trust you that you can do this limit. Because by this point in time, you have done enough suffering. You've suffered enough. You've been through the gauntlet. You can do these types of limits. Now, there are some limits that you still have to do a little bit of work, but these kinds, you're okay. Now, what does the root test say? Well, it says if a to the n to the 1 over n converges to rho, if this is less than 1, we're happy. If this is greater than 1, we're sad. If this is equal to 1, we're confused. So less than 1 means converges. Greater than 1 means it diverges. Equals to 1 means you're out of luck. You have to use a different test. In our case, we're 2/3. That's less than 1. So what's our conclusion? So the sum converges. In fact, we could say it's absolutely convergent, but in this case, there's really no question about absolute versus conditional because everything is positive. So no need to raise that up. All right. You know, doesn't these things seem not so bad now? You're like, wow, why did I ever stress so much about some of these problems? These are fun. I wish I had like a Calc 4 and 5. I could just take calculus every semester. Well, no, not yet. All right, number 12. Find the center and radius of convergence for the following series. And you do not need to determine what happens at the endpoints. So we just want to know where's the middle and how big is our radius. Okay, so how do we do this? Well, what we do is we're really going to think of this part right here as our a sub n. Now, when you're looking for the center and radius of convergence, the big thing is you're going to use either the root test or the ratio test. Those are the two go-tos. That being said, on the final exam, what are we going to use? The root test. How do we know? Ratio test is off. So that's a good way to know. And I know I'm really like crushing your dreams here. You're like, Steve, why do you keep crushing my dreams? I love the ratio test.
So when you're saying that the ratio test is no longer on the test, we would be penalized for trying to use it here.
No, you won't be penalized. I'm just saying that you don't have to know it. Absolutely, there's no penalty. No, we are 100%. If you apply a correct technique and get the correct answer, we are going to give you full credit. What we're saying is you don't need to have it in your arsenal of tools. I don't want you to dispose of it. I don't want you to like go home today and well like I'm sorry ratio test. Me and you had a good run, but I found something I like better. That's not what should happen. And so what should happen is you should, understand all these things, because in the future, there's some reason why at some point engineering wants you to take this class. And I apologize for you non-engineers, but I know that somebody wants you to take this class, and so something that we're learning must be relevant, we hope. So it's good to know these things. Good to know these things. I just want you to not, I guess the reason I'm saying this is not to get you to learn less. It's just, I want you to focus on just the key things that you need, so that it makes it easier for you to study and you have less to stress about. And that's my goal of me mentioning these things. All right, I'm sorry, that was a really long rambling talk. Okay, so to find this, we're going to find, in fact, we find both the center and the radius. We do them simultaneously. It comes all at once by either root or ratio. And sorry, I should have written this down while we were having our discussion. So we take the limit as n goes to infinity of the absolute value of a n to the power of 1 over n. So this becomes the limit as n goes to infinity of, and the absolute value, the only thing that affects is the 3x minus 5. That's the only thing that could potentially be negative. Nothing else has a sign attached to it. So it's become absolute value of 3x minus 5 to the nth power over n squared 4 to the n. And all of this is being raised to the power 1 over n. So this becomes the limit as n goes to infinity. Well, to the nth power, to the 1 over nth power, just simplifies to the 1th power, absolute value of 3x minus 5. Downstairs you have n to the 1 over n squared, and you have 4n to the 1 over n. And 4n to the 1 over n, well, actually I didn't need to write that. 4n to the 1 over n is just 4, so I'll just say 4. Now, side note, what happens to the limit as n goes to infinity of n to the power 1 over n? 1. Yeah, this is just something you should know. And if you need it on the test, just write it to the side, we know this. You don't have to rederive it, just say, we know this. They probably won't even check if you write it down, but it's good to just write it down and say, hey, I have knowledge. So we end up with absolute value of 3x minus 5 over 4. That's our limit. So we go back to what we just wrote down about the root test, because we just did it. This will converge when this is less than 1. So the last thing to do is to figure out how do we transform this into our radius and our center. Well, let's work it through. Multiply both sides by 4. Absolute value of 3x minus 5 is less than 4. Now the good news, this is already to the first power. If this had been like a square or a cube, at this point, square root, cube root, whatever you need to get it down to the first power, you want to have the part that's in front of the x be a 1. Right now it's not. It's a 3. You want it to be positive too. Yeah, that's another thing. But okay, how do we get that to be a 1? Divide by 3. Just divide everything by 3. And so if we do that, we'll get x minus 5/3 is less than 4/3. And now we have our answer right in front of us. We just have to label things. Let's start with the radius. What's our radius? The 4/3. This equals our radius. Where's our center? 5/3. So x minus whatever that thing is, that's your center. And there's our answer. 5/3 is our center, 4/3 is our radius. And that's all it asks us to find. We don't have to determine what happens at our endpoints. And so we stop. Because it's a good strategy. Once you find the answer, you should probably stop. Not that, doing math is bad. It's just that you probably will not get any points. And oftentimes we see people have the right answer and then they keep going. And then we're like, I don't think you knew you had the right answer. We have to take a point off. Especially because they end up circling something way at the bottom. It's like, no, that wasn't the answer. It's this piece way at the top that you started with was the answer. All right. Find the length of the parameterized curve 1/3 times t squared plus 6 to the 3/2, comma 3t, where t goes between 0 and 3. So this is about length. Now we've already mentioned length, so there's two types of lengths you should be comfortable with. So there's the form y equals f of x, and in this case, and this is a less than or equal to x less than or equal to b. In this case, your format is a to the b square root of 1 plus f prime of x squared dx. The other one you should be comfortable with is xt y of t, where a less than or equal to t less than or equal to b. And in this setting, so yeah, a and b represent slightly different things between these two, but I'm still going to use both. This is we ran out of letters. We had to start recycling. So, but okay, in this setting, what do we get? It's the integral a to b square root of x prime squared plus y prime squared dt. If you look at this formula, you actually realize that if you let x of t be t and y of t be f of t, it's immediately the first formula. So the first formula is a special case of the second formula. So the question is, which one should you know? I would recommend you just know both, because I know at least at one part of the exam you should be able to just like recognize formulas. At least I hear there's a rumor about problem 1. So make sure you're comfortable with your basic formulas. If you feel like you really only have a few neurons left and it's late in exam week, at least memorize the second one, because it's slightly more universal. But again, I would recommend you know both. So here, now, once you know the formula, there's not much to it. It's just a matter of being very careful and making sure you work with your algebra, which is not too surprising. I mean, that's been a whole lot of calculus is, let's be very careful. Let's work with our algebra. And if life is good and we've lived a healthy, clean life, the algebra will work with us. And the reason we have to be really careful with our algebra, of course, is because of a square root. If you ever encounter a problem with a square root, your main thought should be either what's inside the square root is going to square, or maybe I can pull enough out of the square root I can substitute. That's almost the full extent of things that you should be able to do. So here we go. The derivative of x. Well, we're going to have the 1/3, the 3/2 comes down, t squared plus 6 to the 1/2 times the derivative of t squared plus 6, which is 2t. So there's x prime. And then y prime is 3. Now, it's a little bit of a letdown, but all right, that's okay. It's all right that it's not so bad. So I took the derivative of x, going to square that, take the derivative of y, square that, adding them together inside the square root, and hopefully good things happen. We can already see good things happening pretty quickly. The 3's cancel and the 2's cancel, so that makes it a little bit easier. So, and I wrote a and b. I'm sorry about that. I should have said 0 and 3. I was too distracted. There we go, 0 to 3. So, what do we have? We have 0 to 3, and when we square this, we're going to get t squared, and then here we're going to get t squared plus 6, because we have the 1/2 squared. So, square root, and I'll go ahead. I think we have enough space. We can take it a little bit slowly. And then plus a 9 on the end. So that becomes the integral 0 to 3 square root of t to the 4th plus 6t squared plus 9. Well, what can we do with t to the 4th plus 6t squared plus 9? I hope so, because that's our goal, right? Let's hope that the inside is a square. Well, I bet you it is. What does it become?
T squared plus 3.
T squared plus 3 squared. Ah, just right. So 0 to 3 of t squared plus 3. Now we're cooking. What's the integral of t squared plus 3?
1/3 t cubed.
1/3 t cubed and 3t. Evaluate from 0 to 3. Well, we plug in 3. We'll get 27 times a third, which is 9, plus 3 times 3, which is 9. And when we plug in 0, we'll get 0. Meaning our final answer is 18. 18 what? Haha, trick question. We don't know. They didn't give us any units. So it's just 18. So that's the answer. All right. Well, next problem. Number 14. You are engaged in your favorite hobby of picking grapes. Well, everybody needs a hobby. All right. And you are working along a particular steep hill. At the bottom of the hill, I guess we should draw a picture. So we have ourselves a very steep hill. So here's our hill. And of course, this is not just any hill. It's full of grapes. So here are our grapes along the hill. All right. All right. Good. Got to make sure we understand our picture. And we should, it's a very steep hill. We're going to get our exercise in there today. All right. So here we are at the bottom. And then we're going to walk up this hill. And we have a bag, right? Because at the bottom of the hill, your bag is empty. So here's our empty bag. All right? And then we're going to get to the top of the hill later on. And our bag will no longer be empty because our bag has now been filled with grapes. And so it weighs 17 pounds. So at the top, you've gained in elevation 20 feet. So here we have 20 feet. And your bag weighs 17 pounds. Now, if you make the assumption that the grapes were added in at a constant rate as you went up the hill, determine the work done in moving the bags and grapes up the hill. So you're only moving the grapes that you put into your bag. Now you might say, does calculus really apply here? In some sense you could argue no, because this is a process which is sort of in some sense discrete. But the amazing thing is we're making this assumption that says, well, even though it doesn't exactly apply, it's very close. And any process which can be modeled with that is good enough. So let's not argue too much about whether or not it applies. We'll go ahead and pretend like it does. So what's happening? Well, here we have another work problem. Now, how do we know it's a work problem? Yeah, because it says the word work, right? It's a pretty good clue. If it says the word work, it's a work problem. Now, how do you do work problems? Well, work problems are always basically the same. Now, the way you compute work is you do force times distance. That's their basic starting formula for work, force times distance. The way that calculus comes into play is it says, okay, what we're going to do is what happens when our force is varying. So what we'll say is that work is the adding up. So adding up is just a fancy way of saying integration in calculus. And what we do is our force and our distance. Now, at this point, it doesn't seem like we've really done anything, but let me explain what the difference is between these two. Here, it would be, suppose I have a force which never changes, and I move it a fixed distance. Then it's easy. I just multiply it together. If I have a 10-pound weight, and I move it 5 feet, that's 50. Okay, so there's nothing much to do there. But what happens if I don't have a constant weight? Maybe I have, say, a bag where I'm putting grapes into it. So at the bottom, it weighs 2 pounds. At the top, it weighs 17 pounds. In between, the weight depends. So now, what we can do is we can say, okay, we'll think of it as the following. We'll think of our force as varying with a location. I'll call it y. And distance is just, we move it up a little bit. So I'm going to think about my work as being, okay, one step at a time. It's like, okay, how much work do I have to do to take my next step? I'm moving up the hill. I need to know my next step. So the key to problems when you have work of this nature is to really get a handle on this aspect right here. So what does this mean? Well, what you need to do is you need to figure out your force, which of course for us really is a weight, because when we think of force, we're thinking pounds. Weight at a given location. So we're moving things along. If you can figure out that right formula, Everything else is super easy for these types of problems. If you cannot figure out that formula, you will not get the right answer. So let's focus on that formula. So for our example, we know that we are going up by 20 feet. So one of the things we have to decide is our units. Where should we put our units? Well, I don't see any strong reason to put units one way or the other. So for me, it just makes sense. Let's start at 0 here, and then the top of the hill, we'll have that be 20. So I'm going from 0 to 20. And now what do I know? Well, at 0, which is the start, the weight was what? 2 pounds. And at 20, which is the end, what's the weight? 17 pounds. So I've gained 15 pounds. And again, I gained it slowly. There's another assumption here, which you'll see there's this sort of phrase. It's almost always built in. Sometimes they have different ways of saying it, at a constant rate, where what that means is that somehow the weight is being increased, or maybe the weight is being decreased, but what's happening is that the weight is varying as we move along, and we do it in a very simple, straightforward way as much as possible. So, what do we think? Well, what that tells us is if we think about our weight here, so here we'll put our y. We have 2 there at 0, and then at 20, we're up to 17. And I do realize that my picture is not very accurate, but that's all right. Constant just means it goes up by a straight line. So, what do we need? Well, what we need to do is figure out what is this line. If I need a line, I need to know the intercept, 2. So the weight, or the force, if you will, at a particular y, is going to be 2 plus. Now what about the slope? Well, we go up by 15. We went over by 20. So what's our slope? 3/4. So what we are finding is, what is the weight of what it is that we are moving at a height y for each y? So at the bottom, when y equals 0, our weight is 2. At the top, our weight is 17. If we said, how much do we weigh when we are 4 feet up our hill? What's our answer? 5. So what we found is we found what's the weight for every height y. This is the hard part of the problem. The rest of the problem now just says, okay, you integrate that from start to stop. So integrate 0 to 20, 2 plus 3 over 4 y dy. And from here, it's not so bad. So we get 2y plus, well, 3 over 4 times y, well, that would be 3 over 8 y squared. Evaluate from 0 to 20. Plug in 0. On the bottom, you're going to get 0. That's good news. Plug in 20. 2 times 20 is 40. Then we get 3 over 8 times 20 squared, which is 400. 8 goes into 400. And that's 50. Times 3 is 150. Plus 40 makes 190. And here we actually can talk about units. What are our units? Foot-pounds. Now, again, if it says include units, make sure you include units. If it doesn't say it, it's up to you. Dealer's choice. We won't penalize you for giving us more factual statements. So, insofar as what are the correct units. This might be why it's your hobby. You know, it's like, okay, I got some good exercise in. Moved up the hill, life was good. All right. Number 15. Find the value for the integral from 0 to pi, x to the 7th, cosine of x to the 5th dx, expressed as an infinite series. Now you might say, well, why are we bothering to express it as an infinite series? And then we look and say, oh, yeah, I don't think I want to integrate that. Because you do not want to integrate that. That is a terrible function. Even though you've ended Calc 2, most functions you still can't integrate. we've essentially just sort of given a handful of more tools, but most of the things we still can't integrate. Now there's a couple of clues here that you don't want to integrate this function. You see this word here, series? That's trying to send you a signal. It's saying you are not going to find this as a function. Forget it. But maybe we can use all these cool things that we've recently learned to help us find a series that gives us the answer. Now, how does this type of problem work? Well, what you want to do is you say, if I want to write this as an infinite series, I'm going to say, let's take the inside here and let's write this as a series. And in particular, as a Taylor series. Or you could do a Maclaurin series, but it's really just the same thing as a Taylor series centered at 0. And once I have that as a series, because remember, how do you think of a series? The way to think of a series is as a polynomial. It's a big polynomial, and then polynomials, then you can integrate and life is good. All right, so that's our idea. So write as a Taylor series, and then you can integrate term by term, and then life is good. So that's how we're going to proceed. So again, how do you recognize these types of problems? You're going to have an integral that looks crazy, but it says find your answer as some sort of a series. Now, I should warn you, it may not necessarily be presented in this type of format. It might be, oh, by the way, come find this thing, and in the process of finding it, you're like, oh, I have this crazy-looking integral. It's like, oh, wait a second. I see that it says write my answer as a series. Ah, right, this is one of those types of problems where I write everything as a Taylor series, and then life is good. Now, when it comes to Taylor series, there's basically 4 that you should know. We've already mentioned 1. So 1 over 1 minus z is equal to the summation k equals 0 to infinity of z to the k. We've used that one already today. E to the z. This is, if you're only going to know 1 Taylor series, no geometric. If you're going to know 2, no e to the z. So k equals 0 to infinity, z to the k over k factorial. And the reason I say this is this shows up frequently. E to the z is a super important function going forward in your differential equations and other courses. The other 2 are sine of z. Now, the way I like to remember this is that sine is an odd function, and therefore the sine is going to deal with the odd power. So it's z to the odd number, so 2k plus 1 over 2k plus 1 factorial. Cosine is an even function, so it will deal with the even power. So I have a minus 1 to the k, z to the power 2k over 2k factorial. So those are the Taylor series that you should be expected to know. You should just have those ready, should you ever have the need arise. All right, well, what do we do next? We need to figure out how to write x to the 7th cosine x to the 5th. The good news is x to the 7th, we're actually pretty happy with that because it's polynomial. We love polynomials. A series is a huge infinite polynomial. What we aren't happy with is the cosine x to the 5th. But we say that's not a problem. See, what we'll do is we're going to come over here and say, okay, I'm thinking of this z as like a box. And whatever I put in there, I just slip into that box over there. So in our case, we're putting x to the 5th. So we're going to put x to the 5th there. So this is, I still have an x to the 7th in front. Sum k equals 0 to infinity, negative 1 to the k, x to the 5th to the 2k, divide that by 2k factorial. And now we're almost done writing this as a series. In fact, you can see we're going pretty quick here. Negative 1 to the k, x to the 5th to the 2k, that's x to the 10k, but we have 7 out here, so we put them together. So it's x to the power 10k plus 7, and now divide that by 2k factorial. So we've rewritten our x to the 7th cosine x to the 5th, our function that we were like, I don't know how to integrate that. But now we've written it in like, oh, this is just a series, and we can integrate those. So we get that the integral from 0 to pi of x to the 7th cosine of x to the 5th dx That's equal to the integral from 0 to pi of the summation k equals 0 to infinity, negative 1 to the k, x to the power 10k plus 7, divided by 2k factorial dx. And because this is a nice series, it converges, and therefore we're allowed to integrate term by term. In other words, this becomes the sum, k equals 0 to infinity, negative 1 to the k over 2k factorial times the integral from 0 to pi of x to the 10k plus 7 dx. And this integral, well, that's not so bad. It's just x to a power. So that's the sum, k equals 0 to infinity, negative 1 to the k over 2k factorial, x to the power 10k plus 8, divide that by 10k plus 8 from 0 to pi. Plug in 0, you get 0. So you plug in pi. And you have that, lo and behold, we get the sum from 0 to infinity, negative 1 to the power k, 2k factorial, pi to the power 10 times k plus 8 over 10 times k plus 8. And there's our answer. Notice that your answer should be a series which does not have any x involvement at all. There's no x. It's completely gone. It's just it's going to be a number. Now, can you use this to actually find the value? Well, the answer is you can use it to get really good approximations, because this will converge, and it converges relatively quickly. With just maybe a dozen terms, you'd have it to a super high degree of accuracy. So that's that problem. All right, that's a good problem. We had one like that, I think, within the last year. These are fun. So this is the last problem. Now, I will preface this problem by saying we're going to do this, and you're going to be like, wow, this is cool. But I will tell you explicitly that this type of problem is not on the exam tomorrow, but it's a really fun application, and it just shows you some things that you can do. I will say that it just barely did not get on the exam. I said the word tomorrow. I should have said next week. It came really close. So this is something which you won't be expected to do, but something which hopefully you can enjoy, and I won't be surprised if you see it again sometime next week, depending upon who your instructor is. So suppose you have 0.166, so it's this fraction, this decimal that keeps repeating. It's 166 repeated over and over again. We want to write this as a geometric series. Now, at first glance, it's not so obvious that it is a geometric series, but how should we think of it? Well, let's just think of it as chunks, because really there's these repeated chunks. And we think about, okay, how do we write each piece? So the 0.166 is really 166 over 1,000, because you just take this and you move the decimal over. The next piece, which is 0.000166, that's 166 over 1,000 squared, because you move the decimal place over now 6 times. 0.000000166, that's 166 over 1,000 cubed, and so forth and so on. So what's happening is that this number here, this 0.166, 166, 166, so forth, so on, that's really the summation starting from 1 to infinity of 166 over 1,000 to the power k. And I'm starting at 1 because notice this is my first term. If I had 0, I'd only have 166. So that's the first part. So I can write numbers like this as a fraction. Now I say, okay, let's find the sum of the series. So if I have a geometric series, remember, how does a geometric series work? You take your first term. Your first term would be if k equals 1. So the first term would be 166 divided by 1,000. That's what you get when you plug in k equals 1. Divide that by 1 minus, what are you multiplying by at each stage? In our case, it's what? 1 over 1,000 is right, yes. And now, if you multiply top and bottom by 1,000, what you end up with is 166 on the top And then downstairs it's 1,000 minus 1, which is 999. And I don't think that simplifies. It might. I don't think so. But lo and behold, if you take 166 divided by 999, you will get 0.166, so forth and so on, which is a great way to end our class. All right. Thank you. Good luck. If you can do these problems, you're in good shape.